Now, for the sake of this video, I'd like to imagine that these bits of Lego are hydrogen atoms. And basically, around the various parts of the universe, there are various bits of hydrogen gas which are sort of spread out everywhere. But there might also be maybe a few bits of helium, and then perhaps, a few of these heavier elements, depending on what part of the universe or what stage of the universe we're talking about. But effectively, what we have is this kind of really large, spread out cloud of dust and gas. And where this is fairly concentrated, this is where stars are formed. And this is what we call a nebula. Now, a nebula is this kind of sort of star-forming region, and all of this kind of dust and cloud, what it does is it starts to come together due to the force of gravity. Now, effectively, as these things get closer together, they lose some of that potential energy and it turns into kinetic energy, just like this mass is attracted towards the Earth down here because they've both got mass. As it loses its potential, it starts to speed up. And what we find is that gravity pulls everything together. And there's this massive force inwards due to their gravitational attraction. And what we find is that this cloud of dust and gas, it comes together into the second stage in the formation of a star, and this is called a protostar. Now, in a protostar, no fusion is happening. But what's happening is that the density in the middle starts to get bigger, and that means things like the pressure increases, and also things like the temperature increases. Now remember, there's an equation that says, maybe for an ideal gas, that E is equal to 3/2 kT. And basically what this tells us is that the mean translational kinetic energy is proportional to the temperature. Well, as these things get closer in, they start to speed up, and therefore the particles are moving faster, and therefore their temperature increases. And we get to a point where gravity is really pulling everything so tightly that in the very centre of this region, we then have the conditions where the pressure's high enough, the temperature's high enough, and then we can actually get these two hydrogens, or I guess by this point the electrons have been stripped off, we can actually get protons to start to overcome their electrostatic repulsion and start to react nuclearly. Is that a good word? These protons react with other protons, and then we have fusion happening. And it's in this part of the star where fusion starts to happen that we have what we call a main sequence star. It's called a main sequence star from the Hertzsprung-Russell diagram, and there's another video up here you can have a look about that. But basically, inside the star, there are two real forces acting. First of all, you've got the force of gravity that is pulling everything in, because these things have mass, and there's this really massive force due to gravity that's kind of holding that star together. But this is kind of counteracted by the fact that effectively what you have inside is fusion occurring. And again, I've got a whole video up here that talks about fusion, about the different steps of hydrogen turning to deuterium and then helium-3. And basically what we have then is effectively a load of like hydrogen bombs going off. We've got these nuclear explosions, and this causes an outwards force. And this is what we call radiation pressure, or the gas pressure. And what we know is actually that if this star is in a kind of nice stable position, it's an equilibrium. The inwards force is balanced by the outwards force. And what we find is that the force of gravity is equal to this radiation and gas force. And this can occur for many, many billions of years. And what we're talking about is as time goes on, the hydrogen maybe starts to get used up as we start to make more helium. And in actual fact, things like our sun, they're losing about 1 million tonnes of mass per second, as the mass is being converted into pure energy, which is then radiated out from the star. But we've got to remember that things like our sun, for example, which is a fairly kind of average sun, it has a mass of about 2 × 10⁻30 kilograms. So it's really, really heavy, and there's a huge amount of stuff in the middle. And it can keep doing this kind of phase of burning for many, many billions of years. And it's only really towards the end of the life cycle of a star that we start to use up the fuel, and then we kind of start to make either maybe things like red giants and white dwarfs if it's a low mass star, or if it's particularly heavy, we can have things like supernovas, neutron stars, and then finally perhaps even a black hole. So have a look at my other videos where I talk about the end life of both low mass and high mass stars. Thank you very much.